All right, in our last video, we were looking at compound inequalities. We saw that there are AND inequalities, and in AND inequalities, you need the two inequalities to overlap each other. You can also sometimes have OR inequalities, and with OR inequalities, you're happy with either of the two regions. You just join them together with a union. Well, now we're going to take a look at something called absolute value inequalities. And just to remember, let me see what I got here. Yeah, let me show you this really quickly. So I need you to remember this fundamental idea. When I have an absolute value, something like this, some mathematician a long time ago just decided that what they wanted to know was not the value of the number, whether it was 3 or -3, but rather how far away that number was from 0. And so these bars literally in English would mean how far away from 0. And that's why they're absolute values. Because if I was standing here or here, in either place, I am 3 steps away from 0. That should be a 0. There we go. So absolute values, that's a quick refresher. It means how far away am I from 0. And so its magical power, if you want to think of it like that, is to turn whatever is inside of there into a positive number. Okay, now I am skipping this part. I just want a good place to work this. Okay. Now, there's some important things to know about solving absolute value inequalities. And this slide this actually only has a few. I wish I had a few more. But the first thing you have to remember, however, is how to solve them if they were an equal sign. Now, if you had an equal sign, what you could do here is, because whatever is in here, it could be a positive or it could be a negative. So hold on, let me go back. So if I turn this into variable world, the absolute value of x is 4. Okay, well, what two numbers could go in there? Well, x could be 4 or -4. So because there are two options, we have to work the problem twice. We work x equals -4 and x equals 4. So we work the problem twice with what we have, and then we work it again with a minus. So when I do this problem here, I'm going to start by just doing the problem that's there, and then I'm going to work it again with the negative sign. Okay, so a quick refresher. So there are a couple of exceptions here, but what should happen when you work an absolute value equation is you should get two answers. Okay? Now, I have an activity that I do in classes that kind of illustrates this. Yeah, I think I'll do that, but let's start by just explaining what this means. If I start with an absolute value inequality that has a less than sign, then what's going to happen is that this is going to turn out to be an AND inequality, just like we saw in our last lesson. And if we have a greater than sign, it's going to be an OR. That's what this slide is trying to say. Now let's get to one, and I don't want to do that. Okay. Yeah, so let's look at this one. Now I'm going to solve this first as if it was an equal sign. Now you don't have to do that, but I'm going to just show you what's happening here. So x minus 5 equals 4. I would solve it again as if x minus 5 is -4. Now I work these two problems. I get x is 9 and x is 1. Okay, so now if you had a number line, you've created, I'm going to mark these numbers here and actually give it a big long line. Now you've created 3 regions, and you could pick any number that are in these 3 regions to test out whether or not the inequality is true in that region. What I mean is this: I'm going to pick 0 over here, going to pick 3 over here, and I'm going to pick 10 over here. I don't know if this will work out nicely, but now I'm going to put this into this inequality right here. So I've got 0 minus 5 less than or equal to 4. Okay, well that's the same thing as this, which we know is just 5. Now, an absolute value works like a parenthesis, so do everything inside of there first, and then make it positive. You can't turn it positive first. You got to do it the right way around. So all of that turns out to be 5. Well, is 5 less than or equal to 4? Is that true? No. So this region is false. You could pick any number and it would always prove to be the case. Let's try a 3 in there. So I've got 3 minus 5 less than or equal to 4. So I get a negative 2 in there, and then I take the absolute value, I'll get 2 is less than 4. Yeah, that's true. And then lastly, I'm going to pick 10. So I'm not going to show my work, but I'd have 10 minus 5 is 5. And so the absolute value, that's still 5. Is 5 less than or equal to 4? No, it's not. So this is false. Now, if you can't remember the trick about that I said on the previous slide, I'll repeat it in a minute. You can always work an absolute value inequality as if it was just an equal sign. Make these regions like I just did, and then pick test points in each one. Now, what we've found by doing this is that the true region here in interval notation is from 1 to 9. See that? We're going between these two spots. That's the true region. I've got brackets because I had equal signs. Now, that will always work for you. The other way you could do this is I solve the inequality twice. I do it once with the less than sign, just like it was there. And now I'm going to do the other one, but it's like dividing by a negative. So I'm going to turn this into negative 4. But if I've done that, I also am going to change the direction of the inequality sign. So work it twice, once as it is, and once with the negative sign and the inequality the other way around. All right, if we work this, we know that this kind, a less than, is an and. This actually showed us as well, but this is going to show us that a less than is an and. So I'm going to graph this again, and I want the x's less than or equal to 9. That'd go this way. And I want the x's greater than or equal to 1. And less thans are ands, so I want where they overlap, and we get the same conclusion. Okay? So you can do it as an equal sign, test it out, or you can do it twice. One with a less than, or once just as it's written, and then you work it again with the negative on the other side, and you flip the inequality. This isn't really what I want to do. Let's go to this one. I may go back to that. So if you want to try this one, is there anything special about this? This is pretty much the same thing. Yeah, this is nothing special. So they're just working this exact same thing again, just like the one we did. We're going to work it once like this, and then once we're going to flip it around and do the greater than sign. So I've got x is less than or equal to 4, and x is greater than or equal to negative 2. Now it was a less than, so that's an and. So we need the overlap region. Now I'm not going to draw the number line, see if you can understand. If I wanted the x's less than or equal to 4, that would go down. If I wanted the x's greater than or equal to negative 2, that would go up. And because it's an and, they would overlap between negative 2 and 4. Okay, so if you ever have, hold on, let me see. I don't want that one. Hold on. Yeah, here's what I want. There's not as many examples in here as I would like. Now, I want to work this inequality. This negative 2, this is not, you cannot distribute it. I know this is like a parentheses, but it's not the same. Only what is inside of here is inside that absolute value. That's the only thing that's magically going to turn positive in the end. So what we're going to do is we're going to treat this as if it was a giant I don't know. So we want to isolate. You'll always do this in algebra whenever there's a square root, something tricky. What we want to do is we want to isolate that tricky part all by itself, and then we'll work on it. So what I mean is this. I'm going to treat it like a giant I don't know. I'm going to divide both sides by -2. Now, if I divide by a -2, that's going to flip the inequality sign. So what is left there, my giant I don't know, it's going to flip it around, it becomes a 3. Now, this wasn't a giant I don't know. It was an absolute value of k minus 4. That's what we really had. So get it down to the problem part. Do not distribute. Now that we've got that alone, we're going to work this again. We've got k, minus 4, we're going to do greater than or equal to 3. And we're going to do k minus 4 is less than or equal to -3. Now remember, this was a greater than. This is going to be an or problem. It'll kind of be obvious to us when we do it. So I've got k is greater than or equal to 7, or k is less than or equal to 1. Just adding, just simple algebra. You work them exactly the same. We saw that in our inequality section. Okay, now this is an or. So put this on a number line. I want 1, and I want everything below it. I want 7, and I want everything above it. So I picked brackets. Now this was an or, so I'm happy with either region. So in interval notation, I start at -infinity. We always go left to right. We're going up the number line. So I have -infinity to 1. And we're going to, oops, sorry, these should be brackets. Hold on, I'm going to write this again. Going up the number line, -infinity to 1. You can never get to -infinity, so a parenthesis. We wanted 1. Now we're happy, we're going to union from 7. We go the rest of the way. And that's our solution. Now you'll see more complicated versions of this. Suppose we had started with something like this. So if we had started with something like this, well, we would do the same thing. We would just work as if this was a giant I don't know. And we're going to get that absolute value isolated all alone. I'm going to send the 5 to the other side, divide both sides by -2, and then I would get to work. Okay, I've got a couple things that I did not know are not covered very well here. Ignore this here. I want to show you some strange things that can happen with absolute value inequalities. Okay, suppose, well, anytime you have an absolute value inequality and you see a 0 on this other side, or perhaps a negative, you need to be careful. Something strange is going to happen here. So I'm going to make all the options that can be strange. Let's see. Okay, so here's what I'm saying to look out for. If you ever have an absolute value inequality and you have a 0 on the other side or a negative, now it's only a problem if you had to clean something up. It's only a problem if you've done all the algebra, you've got this isolated, and then it happens. It's okay to have the negative at the beginning. That doesn't matter. It's only when I've done all the cleaning and the only thing that's left are these absolute values. If you have the zeros or the negatives, you've got to think this through. There's a puzzle going on here. It starts to become a logic problem. And here's what I mean. I'm going to start with this one down here. This says that the absolute value is greater than -2. I see the negative sign, so I'm going to stop and I'm going to think through the logic of what this means. Well, the left, this side is always positive. So isn't this always going to be greater than a negative number? It is. And so in interval notation, I'm going to say that everything is the solution. Okay, now we're going to come up here to this one. We've got the absolute value and we got a negative on the other side. So an absolute value is less than -2. Well, we already said this is a positive. It has to be a positive because of the bars. Whatever comes out of there is going to be a positive. So how can it be less than -2? That's impossible. So it can't be. It's the empty set, no solution. Okay, now let's come over to these options. Let's do this one. Now x minus 3, oh, this is not the one I wanted. Hold on. What I want to do, here's the weird one. X minus 3 is less than or equal to 0. Okay, now we know the less than is not an issue. You can never be less than 0, so that's not true. But you got to be careful because you could be equal to 0. And the way that would happen is if x turns out to be 3. If I put 3 in here, doesn't this turn out to be 0? So this one can never create numbers less than 0, but it could be 0. So we get one solution. Now, how about x minus 3 being greater than 0? Well, yeah, we know this is always a positive, so this is true. Or is it? There is one statement that would make this not true. What if x turned out to be 3? If x turned out to be 3, this would not be true. It would be a lie. And so, the only number that is not allowed in this situation is the number 3. Now, in interval notation, see if this makes sense to you. This is an important idea for later, and what it means is this, that every number can go into this inequality and make it true, except the number 3. We would go to 3, and because it's a parenthesis, we would jump over it, and we'd pick it up again on the other side. Okay, so that's how you solve them. Now just watch out for these unusual situations when you have a 0 on the right or a negative. Now I've skipped some things. Let me see. I didn't really like the order where they were at. This is a pretty useful idea, although I don't usually put a lot of focus on it. Yeah. Okay, that's supposed to be a pound sign. This is how inequalities work here, the absolute value inequalities. Your number x is always away from the number they're talking about, and here's the distance. If this isn't making much sense, here's what I'm trying to say. X is away from the number 2. How far is x away from the number 2? Well, it's within 3. It's always going to work this way. So we have the number. We're comparing it to some number they're interested in. They want to know how far is our number away from their center, is what I like to consider this. You'll see this later in a function section. It'll make more sense. My letter is x. How far is it away from the number they're talking about, number 2? And what is the distance? In this case, what is it within? It is within a distance of 3. Okay, anything else here I want to talk about? I don't think so. That's enough to get you started. I wish I had shown some more. Wish I'd had more examples in here. I'm not sure, that section's kind of small. But everything you need should be in this video, and hopefully that will get you going.